Welcome to Catastrophes. Today we have an interesting discussion coming for you. We're actually going to be talking about landslides, but also tsunamis, and maybe how one can force the other to happen. And to have that discussion, I've brought Dr. Dan Shugar, who is a geomorphologist and an associate professor in the Department of Earth Energy and Environment at the University of Calgary. Before I go into your background, Dan, how are you doing? And how is it in Calgary today for you?
Yeah, doing well. I'm on sabbatical right now, and so life's pretty good. Can do, spend a lot of uninterrupted blocks of time doing the things that I really enjoy. So that's pretty nice. And yeah, it's definitely looking forward to spring whenever that arrives.
Yeah, well, that's exactly right. Well, yeah, good for you. Sabbatical means you've got some interesting projects, I suspect, maybe coming up if they haven't already started yet. I
Hmm.
want to dig into those in a minute, but I figure the background, your bio is worth digging into itself. So, as I mentioned, you're an associate professor at University of Calgary, but you also are the director of the Water Sediment Hazards and Earth Surface Dynamic Lab, and or sorry, Dynamics Lab. What do you do there, and what's the kind of stuff like? Are you guys creating videos like maybe we're going to show in a bit, or what kind of work do you guys do at that lab?
So the Watershed Lab, Water Sediment Hazards, Earth Surface Dynamics, is basically my research group. When I was starting out as a faculty member about a little over a decade ago, I wanted to have a Twitter handle that sort of could be used for all of the work that I was eventually going to do as a prof. And I liked how European projects often had kind of clever acronyms. And so I came up with this acronym, Watershed Lab, which, just the word itself, watershed, describes, the environments that I like to work in, steep watersheds in particular, but then was, this kind of funny acronym. And so, yeah, it's nothing fancy. It's just my research group, undergrads and grad students and postdocs and myself working on a whole variety of projects to do with Earth surface change, and in particular, really rapid Earth surface change, often resulting in things that go bang. And, that's kind of where we get excited.
So the idea for Catastrophes, this podcast, was yeah, I should do an acronym, and I came up with a few, but I just thought could do that acronym, or I could just call it something, and then there's nothing behind it at all. So I commend you on the thoughtfulness of that. I really like that idea. I should have.
Thank you.
Um, yeah, that's really cool. So you're a geomorphologist by trade, I take it. What brought you to landslides and just geomorphology in general?
Well, when I was, going back almost 30 years ago now, when I was an undergrad, I actually started off in a natural resources management program at University of Northern British Columbia. So the university was only a few years old at that point. I still have my student ID card, and I've got a very low student ID number. And so that program, at least the sort of focus that I was in, which was recreation, outdoor rec, was the idea was to train people to become park rangers or to manage a ski resort, that sort of thing. And I took a class in geography in my first year and really fell in love with it. Fell in love with these incredible landscapes that we were seeing all these photos of, and I decided, I don't care what I do, but I want to work, there, whatever there was, whatever cool landscape. And so I transferred into geography, and I had, every university in Canada just about has a geography department. So I basically moved back to Ontario, where I had grown up, and finished my degree at Carleton. And in that process, took this course called geomorphology. And a buddy of mine said, "Hey, you should take this course. You'll like it." I don't know what that word means either, but it's fun. And so I took, this third-year course, geomorphology, and just loved it. And one thing led to another, and here I am.
That's brilliant. And I have to get this out of the way because on previous episodes, and I know some of my viewers will remind me, we have volcanoes, so we have volcanologists, we have seismic, earthquakes, we have seismologists, we have landslides, landslideologists, right? No, I actually learned on air, live. It's not that.
Yeah, so geomorphologists. I was actually giving a talk to my daughter's fifth grade class the other day, and I went through the kind of the etymology of the word. And so if we break it down, geomorphologist.
Right.
So ologist is somebody that studies something.
Hmm.
Geo, earth or rock or whatever, and morph kind of has two meanings. It could be changing, so like a caterpillar morphs into a butterfly, metamorphosis. But it also could mean shape. And so really what a geomorphologist does is study how the Earth's shape changes. And so some of us are interested in kind of really, really small micro, millimeter scale changes on, sand ripples or something like that. And others will work on, entire mountain ranges, how those evolve over millennia or over, millions of years. Most geomorphologists, I would say, although, I haven't actually counted, most work, somewhere in the middle, on sort of, how rivers evolve over, decadal, centennial, millennial timescales, or how mountain slopes evolve, or, whatever the case may be. And so I'm interested in a whole variety of things. I've worked on rivers and lakes and coastlines and mountains and glaciers and permafrost swamps and all sorts of things. And but the steep environments are where I sort of am most drawn to, partly because I enjoy just being in mountain environments, but also because they're very dynamic. They're changing very rapidly, not only on geological timescales, but on human timescales as well.
Mm-hmm. Yeah, when we think about like the threat of GLOFs or glacier lake outbreak floods and different kinds of rock slides, different kinds of landslides. Yeah, all around the world, they're happening in places that are densely populated too. So this is a very timely episode, timely hazard.
Yeah, and 15 years ago or so, I was much more interested, I think, in kind of blue sky science, like just answering questions that just satiated my curiosity, without necessarily any kind of applied angle or applied element. And even though I was working on landslides during my PhD, but it was in the Gorkha earthquake in Nepal so what was that, April 2015. And I was involved in a global kind of scientific response to that disaster. And that was really the first time I think that I could sort of use the skills and expertise that I had generated over the previous decade or so on a real applied problem where in the days and weeks following, like, people's lives were totally upended, and working towards helping with initially with response efforts through the United States Geological Survey and NASA, eventually into sort of recovery efforts. And that kind of, even though I'm still interested in that blue sky science, just because answering questions just because they're interesting, probably the most impactful work is, when there is some kind of direct societal implication or benefit.
Yeah. That's why I'm here, right? Like, those are the things that are most interesting. And from the people I've heard talk about, different disasters, that's the reason often they're listening to this podcast is, what's the human implication for this? What does it look like 2 years, 5 years, 10 years down the road?
I was talking about this, like, there's sort of a movement in the hazards and disasters community to get rid of the word natural disaster.
Yeah.
because
Very good.
there's no such thing.
Mhm.
Um, by definition, disasters are not, the hazard may be natural, but
Mm.
the implications, the repercussions, the impacts are not. But one of the things I think that's a little unfortunate is that we think of those impacts purely in human terms. We think of them only if they kill or hurt people or
Mm.
impact or destroy infrastructure, villages, pipelines, whatever. We don't tend to think, we don't classify an event as a disaster if it was an ecological disaster, but not
Yeah.
necessarily a human one. And
Exactly.
I think that's short-sighted.
Yeah.
But
And
I
it's
don't
especially
know.
short that's short-sighted because you have good insight into when there's a burn or a fire and then it's destabilizes the slope. Well, we actually got to call the geomorphologist in because there might be a landslide that
Mhm,
comes
mhm.
because of that. So
Yeah.
that's a great
Well,
point.
you know, so in 20, what was it, 2020, I think there was a fairly big landslide in coastal BC that went into a glacial lake and caused a tsunami and then an outburst flood, and eventually reached the ocean. And nobody was hurt in that. No people were hurt. I think there might have been some logging roads that were destroyed, maybe a kind of a temporary or a non-permanent cabin, or not permanently occupied cabin.
Right.
But there was lots of salmon habitat that was destroyed,
Mm.
and that, or at least heavily altered, and that certainly has implications for First Nations in the area. But the damage was done to the salmon bearing streams. And so, would we classify that as a disaster? Probably not, but maybe we should, because that habitat was destroyed.
I love the direction this is going, and for people who are new, we don't use the word natural disaster. Well, I certainly don't, and most of my guests have not either, um, because it often implies that disasters are bound to happen, that people don't really have the agency or the ability to reduce their effects. And when we study disasters, typically they're made up of three parts. Quickly, the hazard, which is why Dan is here, the vulnerability, which is often community, and often we describe it as a snapshot of what makes people susceptible. It's much more than that. And if you continue listening on, you'll probably learn from me and others that there's much more to vulnerability than just that snapshot of what makes you susceptible. And then there's the exposure. And those three things, they make the risk. And then the risk is all that kind of stuff. So I talk a lot about no natural disasters, and I have an entire episode on it. I think it's number 16 if you are interested. But this is going to be a great conversation if you're already dropping the no natural disasters campaign. And I'm happy to have you.
I'll add one more plug there. I collaborated with a team a year or two ago on a paper. Forget what journal it was published in, but I can get the link. And it was about the sort of repercussions or the impacts of hazardous events on various ecosystems. And we pushed for, or I pushed for, the title to be to reflect this, not controversy, but to reflect this kind of issue of natural versus unnatural disasters. And so the title, I forget exactly what it is, but it's something like natural disasters, blah blah blah. But then parenthetically before the natural, we have un.
Yeah, perfect. Those are my favorite ones. You're gonna have to send me that, and I'll send you a note after because
I will
I
do
like
it.
to read things like that. So a pretty great background already, but you're the director. You've got a watershed, which is great lab name. You've probably got a lot of other really interesting stuff, and I've asked this question before, and it's actually spurred like a lot of email chains back and forth. So I have to ask it to you. What's the next project that you're working on? Or
Mm.
what's the thing that excites you most about the next project?
Oh, that's a good one. I mean, working in this realm, sometimes it's called ambulance chasing science.
Hmm.
whenever some big event, some big geophysical event happens, then, there's a group of us around the world that kind of jumps into action and goes and tries to figure it out. And those are, of course, hard to predict. If we have a big earthquake or a big landslide or whatever, that could happen today. And, I have no idea. And maybe tomorrow I'll be deep into that. But in terms of sort of planned projects, we're working. My group and a colleague from SFU, we have a project with CP Rail where we're looking at landslides along their sort of corridor in just on the west side of the Rocky Mountains and then through Rogers Pass to look at how mass wasting of different kinds of landslides, debris flows, etc., how that coarse material is ultimately we want to know is that coarse material when it gets sort of accumulates in culverts and bridge piers and that sort of thing, should it be moved into the main stem of the river from a fish habitat perspective, or should it be removed? So anyway, we're just getting started with that. And then in a few weeks, I'm heading to Europe to do a few things, but one of them is to work on a very large permafrost related landslide in Svalbard in Arctic Norway.
Oh, very good.
And so that one is exciting because I've never been that far north, something like 75 degrees latitude. And but it is a potentially tsunami-genic landslide as well, if it were to collapse catastrophically into the fjord. Wow. And then a few other similar kinds of projects, landslide tsunami things in Yukon as well as in southern BC.
Well, I'm going to want to hear about your trip to Svalbard after you get back. But staying on topic today, we are talking about Alaska, and we are talking about landslide-induced tsunami, tsunami-induced landslide.
No, first one was right.
Yeah, the first one was right. So basically the process of a tsunami being generated from a mass amount of rock, the landslide, falling into the water. And you just released a paper, 481 meter landslide tsunami in a cruise ship frequented Alaska fjord. What a good title, first of all. So we got to talk about, first of all, why Alaska? Like, of all the places, Alaska sees a lot of these landslides and then that cause tsunamis, or what?
Yeah. Alaska, like much of Western Canada, is characterized by pretty steep terrain, glacially carved terrain, lots of loose sediment all over the place, seismically active, et cetera, et cetera. So there are lots of opportunities for landslides to occur, really almost anywhere in Western North America. Mm-hmm. In Alaska, unlike in BC, and this may surprise people, Alaskan fjord. So a fjord is basically a valley that's been carved by glacier action, but that is at sea level. And so, very steep-sided valley that is the bottom part of it is drowned by the sea. Mm-hmm. And at the head of a lot of those fjords in Alaska, there are what we call tidewater glaciers. So these are glaciers where their snout, their terminus, ends in the ocean and is floating in the ocean. In BC, we don't have any, or maybe I should say in Western Canada, we don't have any tidewater glaciers. Huh. We have glaciers near the terminus or near the head of the fjord, but none that actually end in salt water. We do have tidewater glaciers in Canada, but they're in the Eastern Arctic. So Baffin Island, Ellesmere Island, that sort of thing. But in Western Canada, we don't have any. We do have glaciers that terminate in a lake or a river, but actually, I don't know. Yeah, there are some that terminate in rivers. And of course, those can generate a tsunami as well. Mm-hmm. But really, here what we're talking about are these landslide, glacier-related landslides into fjords. Mm-hmm. And so Alaska has, coastal Alaska anyway, has a lot of steep terrain, a lot of fairly recently deglaciated terrain, which, is sort of responding to the glaciers retreating and sort of those slopes. You can almost think of them as kind of relaxing from being eroded and then held up by the glaciers. And of course, at the bottom of them, and the fjord itself, the fjord water is important because if there was no water at the bottom, if it was just a dry valley, the landslide happens and falls onto the land, and who cares? It's done.
Yeah.
But because there's this liquid target at the bottom, that can then trigger a hazardous cascade, a domino of impacts that will travel much farther than just the landslide itself would.
And I think a good conversation is going to be talking about that domino and really how that looks not only to human settlements but to cruise ships and the cruise ship valley that you guys did your research on. So obviously a great title already. This is an open access paper, right?
I'm fairly certain, certainly. So, today, as we're recording, it's June 11th. The paper's official typeset, copy version came out in today's issue of Science. But, it sort of came out online about a month ago. And until now, you could just click on the link and read it. I'm pretty sure that's the same still today. So, yes, it should be open source. As of this morning, it had been downloaded 94,000 times already.
Wow.
So, lots of people out there interested in reading about it. And, if a listener or viewer can't get a hold, feel free to send me an email and I'm happy to send a copy along.
Oh, brilliant. Yeah, perfect. So that's what we're going to be talking about today is this, which is such an interesting topic because it seems as though in the last, maybe call it 5 or 6 years, we've seen a lot of landslides within the media, but very few landslide causing a tsunami or landslide generated tsunami, as maybe we'll call them landslide tsunamis from here on out, just for not as many words. Seems like there's been more and more of them. And obviously we got to talk about climate change. We got to talk about all these different things. But I guess just what makes a landslide happen? We have to start the basics, right? Why do landslides occur?
I mean, the simple answer is gravity. Mountain environments, mountains are when they're young, they're being built by tectonic forces or volcanic forces, building these mountains up, and then at the same time there are various forces trying to tear them down, and the competition between those two sets of forces determines whether a mountain is getting bigger, like the Himalaya, are growing, or getting smaller. Like the mountains in Eastern North America, or most of the mountains in Eastern North America. And how do they get smaller? Well, ultimately the cause is gravity. If we had no gravity, even if an earthquake happened, the rocks wouldn't fall downhill. If we had zero gravity, but we do, right? And so rainstorms, freeze thaw processes, water turning to ice and then back into water, earthquakes, all these things work with gravity to make mountains smaller. And so on the West Coast, we don't see this too much in the Rockies, but on the West Coast, where it's much wetter, debris flows are very common occurrences. Hundreds and hundreds of them will happen in any given year. And these are much shallower landslides, just in what we call the superficial materials. So not the bedrock exactly. There might be a little bit, but mostly, the sediments, the soils, the trees that drape the bedrock of the mountain itself. And they tend to be fairly small. They can still be destructive and result in disasters, but they're pretty small events, few thousand cubic meters, few tens of thousands maybe. On the opposite end of the spectrum, we have what are called rock avalanches, which are much more dramatic. The whole mountain slope failing. These are bedrock failures. Typically, the threshold that we call it a rock avalanche is about 1 million cubic meters. So these are pretty big. If your listeners have driven, through Crow's Nest Pass, gone through Frank slide, or driven through Hope, not on the 1, but on the, what would that be, the 3, I guess. You drive through the Hope slide. These are large rock avalanches, very small in comparison to the one in Alaska that we're talking about, but nevertheless, tens of millions of cubic meters of rock that collapse from the mountain slope and get pulverized very quickly. And so, this formerly solid or mostly solid mountainside turns to, dust. Many of the particles, in fact, probably the majority of the particles by number, are kind of sub-micron, atomic size particles, very, very tiny.
Wow. So let's talk about this landslide in Alaska. I also have a video I'll show in a couple of minutes as I'm getting it prepared. But what do we see and what happens with it in the volume?
So this landslide was 64 million cubic meters, plus or minus. There's some error associated with that measurement, but about 64 million cubic meters. And one of my British colleagues calculated that would be enough. If the Great Pyramid of Giza was like a giant, salt shaker or something, and you could pour all this landslide debris in, it would fill that up 24 times. So,
wow.
A lot of material, certainly not the biggest, we've ever seen. And in fact, not even the biggest that we know of in Canada, but, pretty big. And so you can imagine if you threw 24, Great Pyramids of Giza into, a big swimming pool, it makes a big splash. And so in this case, that swimming pool was one of these fjords called Tracy Arm, pretty deep, several hundred meters deep at its deepest point. And the result was this very large tsunami, the second tallest ever recorded.
So on the screen is an animation. Dan, if I'm not mistaken, you and your colleagues created this, and
yes,
we're gonna watch this. It's about a 2-minute clip, but it really gives a good illustration of how it unfolded. So please take us through it.
Sure. So this numerical simulation, this is a physics-based model, was done by Pat Lynette from the University of Southern California. And what you're seeing here is as if you were on a jet ski at the water surface. So you see this landslide starting, and you're like, oh boy, I got to get out of here.
Wow.
And you start. Oh, it's paused there. You start going, and basically, in the terrain in the background there is a satellite image from a company called Planet in San Francisco. And it's a post-event satellite image. So in other words, what we're looking at is how the terrain, not the landscape itself, but the what's covering the terrain, the trees, etc., how it would look after the tsunami. And so as the video progresses, you'll see kind of like a bathtub ring around the fjord that represents all of the trees that were clear cut as the tsunami went through. So right now, we're being chased by this 100-meter high breaking wave, traveling something like 250 kilometers an hour, and now we're dead.
Wow. And we're on a jet ski.
Well, pretend jet ski. So, in reality, of course, there's no way any ship would be able to survive, that breaking wave that close to the source. 5-6 kilometers out the fjord, a ship might be able to survive. The wave would have been substantially smaller by that point, but it would nevertheless still be a terrifying experience.
Yeah, just to go back, like right there, you can kind of start to see like the height in proportion to the mountainside, and it is as big as a mountain. So maybe the title doesn't lie.
No, so the landslide itself, that from the highest point of the landslide to the ocean, which was not the bottom of the landslide, because probably some material did begin underwater and moved, with the whole slope. But that's a vertical kilometer.
Wow.
And then, so the wave itself in the sort of open part of the fjord here, that was not 500 meters high. That was probably about 100. But as the water rode up the opposite shore, splashes up the shore, that's where we measure a height of 481 meters above sea level.
Wow.
And so, off to the right of the frame here, in 5, 10, 20 seconds later, or whatever, the water, you'll see the water kind of rising up the shore right there. It'll go up, it'll splash up the shore to that height of nearly 500 meters above sea level, which, as I said, is the second highest. Or maybe we don't actually see it splashing in this video, but there are some other ones where you see it. Second highest tsunami ever recorded.
Oh, wow. Great animation, first of all.
Here we go.
Yeah, wow.
Way up the fjord wall there. 500 meters, like that's just a terrifying height. I'm in Calgary, and the Calgary Tower, which is not as, I mean, I guess it's as tall as it always was, but there are lots of other buildings that are taller. That's only 190 something meters, 197. So, the max run up of this wave was 2.5 times the height of the Calgary Tower, wow. Almost the height of the CN Tower. Now, that's not to say that if a giant landslide hit Lake Ontario that you would have a 500-meter wave. You wouldn't. Yeah,
exactly.
Because these landslide tsunami, they're so big because of the shape of the terrain around, in the fjord. In a flat landscape like Southern Ontario, it would be a very different story. But the wave, to give people a sense of scale, if you were in that restaurant, at the top of the CN Tower, that would actually have been submerged here.
Wow. That's a really good description. And it was one of the questions I had thought of and didn't want to ask is, why are these tsunamis so much, I guess, higher in these areas? It's because of the terrain around.
Yeah, that's right. So, as water moves around the oceans or in a lake, we see breaking waves when that water or the energy in the water gets towards shore, and that wave energy begins to sort of feel the bottom of, because the lake is getting shallower. And as it feels the bottom, as the lake level or the ocean level gets shallower, then the wave begins to grow in amplitude and height, and eventually it breaks. And so, in a sort of a traditional tsunami, like the Tohoku earthquake tsunami, for example, in 2011, we have an earthquake, subduction zone earthquake offshore, and, the water is displaced in that case, sort of outwards in all directions. But, in the open ocean, it's traveling unbelievably fast, like a jetliner, but the amplitude of the wave is not that big, but it's got a tremendous amount of water that's, being moved along. But when that wave gets to coastline, of course, first the water will retreat and go back out to sea, but that's when the wave gets big. In the Tohoku earthquake, or in any sort of earthquake triggered tsunami, the wave will rarely get above maybe a few tens of meters. In these fjord landscapes, however, where the topography constrains where that water can go, it's a very different story. And so, I like to think of it like, if you've got a kid, 6-year-old kid or something, and they want to take a bath, they want to jump into the bathtub. They jump in, right? They weigh, 20 kilos or something. They jump in, and that water's, pushed aside as they enter the bathtub, but that water can't move outwards infinitely, right? It's constrained by the sides of the tub. And so the water, the tub is longer in one direction, so the water can move out that way, but otherwise the water really can go upwards. And so in a fjord environment, in the case of Tracy Arm, we have, not vertical walls, but pretty damn steep and pretty tall. And the fjord is very, very long, tens of kilometers long. And so the sort of easiest place, so to speak, for the water to go is upwards.
Wow. It's like a bathtub.
Yeah. I mean, it's like a gigantic 300-meter deep bathtub with walls above the water that go up, more than a kilometer.
So, and the speed of which these things happen too is something I'm also kind of drawn to, just with when we think about warnings and whatnot. I think we'll talk about that in a minute, but the triggering of the landslide and then kind of the immediacy of how quick that tsunami is like seconds, or is it minutes? Like,
Yeah, so I'll answer that question in a minute, but I want to pick up on one of the words you said. So triggering.
Yeah.
So in this case, the landslide triggered the tsunami, but there isn't necessarily anything that triggered the landslide itself. And so
Mm.
we in the landslides science community we differentiate between triggers and what we call sometimes called preparatory causes or sort of underlying causes. And
Mm.
so a trigger we typically think of as some discrete event, like an earthquake, like a really sudden major downpour, that sort of thing. And some landslides will have a specific trigger, but sometimes they just happen. And we don't necessarily understand why, but a straw that breaks the camel's back sort of thing. But they always will have some kind of preparatory, underlying set of factors that predispose that slope to failure. And that might be because they're steeper than they can really keep themselves upright. It may be gradual pore water pressure increase, because it's a wet environment, whatever. So anyway, just wanted to clarify that. In the case of this Tracy Arm landslide, so that video, that animation you showed, that's real time.
Oh, okay. We're gonna watch it once more then, because that
We did make some
wow.
sped up ones for social media because most people, if they're watching this, they'll think it's just a still image at this point and they'll move on.
Yeah.
So
Oh,
we know how long this part took because we have data from seismometers, and we can constrain the way that. So there you can see that trim line around the fjord there, and that's on the order of 100 meters above the water, normal sea level. So we can understand how quickly the tsunami traveled and sort of evolved out the fjord based on those trim lines. And so the model was built. So basically what we do is we take some satellite imagery, high resolution satellite imagery from right after the event, and we map out those trim lines. And that's looking more or less straight down from the satellite, hundreds of kilometers up in space. And then we can extract the elevations of all of those trim lines, and then we run the model, which is physics based. You say, all right, you have a landslide of this particular shape, of this particular mass, of this particular volume, falling from this height, entering the fjord. And if you know the bathymetry, the shape of the water, or the shape of the valley below the water, you can create a model. Doesn't mean it's correct, but you can create a pretty model. And so what we do is, or not me, but Pat Lynette from Southern California, he'll run the model, and then we'll look at how well it matches those trimline elevations and the trimline sort of maps that we digitize from the satellite imagery in a GIS, and then tune the model. So we'll go back and say, okay, well, maybe we have, maybe the volume isn't quite right, or the center of mass isn't right, or the bathymetry isn't quite right to match the actual observations. And in so doing, then we can understand the physics of what's going on in these landslides and sort of converting that energy into a wave.
Wow.
So it's not just a pretty animation. It is actually our best guess at what actually happened there.
That's just the speed of it is quite alarming, right? Like it's very
I forget how quickly Pat made the jet ski go, but it's very fast. And and you get taken out within 30 seconds or something of the wave starting. And yeah, I mean, that should be eye-opening, I think, to anybody who goes into these fjords. And I'm not suggesting that nobody go into fjords, right? That's not appropriate and not I don't know, not a good idea to avoid these environments entirely. But the things happen quickly, and if you are at the head of the fjord, whether in your own recreational vessel or in a cruise ship or a fishing boat or whatever, and you don't have however long it takes you to get out of the fjord, if you don't have that much warning, you're in trouble.
Yeah, that's a nice prompt to move to warnings, but I'm not going to take the perfect opportunity to shift. We're going to actually just shift, talk about the word trigger before, which I think kind of fits nicely with something that I always like to provide a brief overview and try to maybe reduce the amount of misinformation out there about climate change.
Sure.
So I want to ask, how is climate change influencing landslides specifically?
So, as I said earlier, there are a variety of kinds of landslides. We've got those like surficial, debris flow, that sort of thing. And, for those, rainfall would be one of the main triggering mechanisms. And so if an area is going to get, more precipitation or less precipitation, or maybe precipitation at different times of year, or maybe it's the same precipitation over the course of the year, but it's in shorter bursts. All of these things could influence how the landscape responds in terms of debris flows. In these rock avalanches, which, in the case of the Tracy Arm one, was something like 200 something meters thick, rain is unlikely to be or much precipitation, moisture is unlikely to be making it down onto that failure plane. But maybe some, especially if there are some pre-existing cracks in the bedrock. In this case, this landslide was what we call a wedge failure, and it's sort of textbook. And so you can think of like, I don't know, I've got my blurred screen on here. I don't know if you'll be able to see it, but I've got my notebook here, and I've got two planes, and if those are weaknesses in the rock, that's a preferential place for the rock to slide. And in the case of Tracy Arm landslide, it was a perfect wedge. In fact, the best textbook example I've ever seen.
Wow.
And so if some pre-existing weaknesses in the rock existed there, and Southeast Alaska is a rainy place, and so maybe some water did get in. But generally speaking, for these really big rock avalanches, I don't think rainfall is a main contributor, but perhaps one of many. But climate change generally. So with climate change, we're really changing two main things. Temperature and precipitation, and in any given location, doesn't necessarily mean warming everywhere at all times, but more extremes, more erratic kind of patterns in precipitation and in temperature, et cetera. But in these glaciated mountain environments, we have this other player, which are those glaciers. And so, glaciers, like in an introductory physical geography or geology class, when we talk about introduced glaciers, we often describe them as like a checkbook. You've got, maybe we should introduce checkbooks to your younger listeners, but, a bank account. So you've got a part-time job. So you've got money coming in, from this job, and then you spend money. You've got rent, you've got groceries, you've got, going out on Friday, whatever. And if you have more coming in than you have going out, then your bank account grows. If you're spending more than you've got coming in, then you've got a problem. And glaciers are essentially the same. And so the income, the money from the part-time job, that is by and large precipitation. So, snow falls and accumulates, and over long enough times that turns to ice, and, the glaciers grow. But at the same time, liquid precipitation, rain, and high temperatures, above 0 Celsius, cause a loss of glacier ice, whether through melting, whether through calving, which is chunks breaking off. And so over the course of a year, the balance of these factors, the income, the precipitation, the snowfall, and the spending, the loss, the melt, et cetera, determine whether a glacier is growing or shrinking. And so at the moment, for the last 50, 100 years, most glaciers around the world have been shrinking, right? Because temperatures have been by and large rising, not only, in summer, but also in winter. And, precipitation patterns changing as well, et cetera. So anyway, back to Tracy Arm. So we have a tidewater glacier in the valley bottom, and I'm not going to get into why tidewater glaciers are a little bit different than land terminating, we don't have enough time for that. But basically, the ocean is warming, the air temperatures are warming in this part of Alaska, like most other places, and the glaciers are retreating. And in this area, basically all the glaciers are retreating, and when they do that, they expose these rock walls. And so the walls, as the glaciers are really active, when they're healthy, they're advancing, they're incredibly efficient erosional agents. So they're basically scraping, over eons, scraping away at the mountainsides, causing them to go from like a V-shaped valley to more of a U-shaped valley. So they have much steeper sides. So if you think of Yosemite Valley or Lauterbrunnen in Switzerland, these are these classic, very steep-sided, what we call U-shaped valleys. Now, just like a sandcastle, you go to the beach, make a sandcastle. Sand doesn't like to stay vertical, right? Wet sand will stay quasi-vertical for a little while, but sand has a natural, what we call angle of repose, where if you pour some sand out onto the ground, it will make a cone. And no matter how big you make that cone, you keep on pouring sand, those angles will always be, the same within a degree or so. Wow. And rock, it doesn't have an angle of repose in the same way, but it doesn't like being too steep. It wants, because gravity is trying to tear it down. And so these glacial valleys, these fjords, are sometimes what we call oversteepened, and so they're steeper than equilibrium would allow them to be, and so they want to get back into equilibrium. If I can anthropomorphize a mountain, but the reason that they often don't collapse when the glacier is there is because the glacier is helping to hold them up.
Yeah,
and so this idea of what we call glacier debuttressing is. I don't know if I would say controversial exactly in the geological community, but is probably a little bit unsettled. Like we talk about glacier debuttressing, but it's an area that we haven't really studied that extensively. Like what's actually going on in these mountain slopes. But anyway, we remove the support from these valley walls, and what we often see is those collapse.
Wow.
So that's one climate angle. We know in the Tracy Arm area that 100% of the post-industrial era warming is due to human activities. 100%. We don't know 100% that it's due to warming. We know that 100% of the warming is due to that. And I think that's an important distinction. And we go into this at length in the paper.
Nice.
But there's another climate angle that I kind of hinted at earlier that I think is important here. In these glacial landscapes, as the glaciers retreat, whether by human exacerbated climate change or, by natural variability, they uncover, they produce new landscapes, right? These recently deglaciated valley bottoms and slopes. And those valley bottoms often are, they're lumpy. And sometimes they hold liquid water, whether that's because it's a lake or the ocean. And so, in other words, as these glaciers are retreating, they're leaving behind all of these little targets. Sometimes it's a big target, which, like the Fjord example, but sometimes they're smaller, like glacial lakes. And, from hundreds and hundreds of studies from glacial mountain ranges all over the world, we know that these glacial lakes are increasing in number and in size. And so think of a valley that has no glacial lakes or a valley that has lots of them. If you have a landslide in either one of those valleys, the probability of it hitting a lake or sort of causing some kind of secondary hazard or tertiary hazard is much higher in the one with the glacial lakes, because there's all those lakes, right? That's not rocket science. And so my colleague Martin Geertsma, who's with BC Ministry of Forests and a co-author on our paper, he once said, when we were working on a different landslide tsunami actually in Alaska a decade ago, he said something about how the climate change is rearranging the landscape elements. And so it's not that the mountains themselves are necessarily moving. I mean, they are moving, but they're not like moving around a ton.
Yeah.
But parts of the landscape, the characteristics of the landscape, the pieces of flair that decorate the landscape, whether that's forests, whether that's lakes, etc., those are changing, and that's changing the hazard and ultimately the potential risk.
Wow. Before I forget, this is a plug to, if you're interested in melting glaciers, I interviewed Dr. Chris Kavanagh from the University of Alberta.
Jeff Kavanaugh.
Yep. Sorry, Jeff. Yeah, I don't know why I said Chris. In November, I think that was episode 41. So if you're interested, please give that a listen. He's got a lot to say, and I learned a lot just about things so out of my wheelhouse that are so interesting when it comes to disasters and the hazards and how they happen.
But yeah, Jeff's a good guy, a great scientist. We worked together on another disaster in India. 5
we
years
talked
ago.
about that one.
Yeah.
Yep. So let's move to the things we can do about landslide tsunamis, which is hopefully some form of prevention mitigation. Given they're just so remote, I suspect mitigation is kind of not really something we're thinking about. There's just not enough people. We can't pay for everything. So we probably have to focus more on prevention. Is that a fair assessment?
Probably. I don't know. There's a few things that are interesting in what you said there. Like, these landslides being remote, that is on, as the, what am I trying to say? That is factual. They are in remote environments, but at the same time, they're not remote. At least these ones in coastal Alaska. And the reason I say that, I like to think of them, and this has only really been kind of becoming more well formulated in my head in the last few weeks. They're intermittently remote, and so these cruise ships that go up and down, coastal Alaska, leave from Seattle or Vancouver, whatever, go up to Anchorage or something, stop in at all the little towns and go into the fjords and see the glaciers. These aren't your grandparents' cruise ships. These are, well, I mean, your grandparents might go on them, but these are not the cruise ships of yesteryear. These are floating cities. Yeah. Some of them that actually go into Tracy Arm and Endicott Arm, which is the next one to the south. Some of these have 6,000 people on board.
Wow.
And that's a town, right? And so if you have, in the summer months, if you've got 3 or 4 cruise ships going into these fjords a day, which we do in Tracy Arm,
wow,
that's a lot of people. And so, yes, they're remote in that, there's no cell service, but they're not remote seasonally, right? There's a lot of people in these fjords. And that's, that's an interesting kind of thought experiment. Well, how do you deal with that? So, on the mitigation side, well, okay, how might we deal with that? So in BC, in southern interior, there are a few extremely large moving slopes, like gargantuan, orders of magnitude bigger than Tracy Arm, and they would be tsunamigenic if they went. They would produce tsunamis if they failed what we call catastrophically, which basically just means fast. Doesn't mean in my community doesn't mean makes a catastrophe. Just means happens instantaneously. Wow. And these are in the Revelstoke area, right above reservoir. Wow. And BC Hydro knows about them, and one of them is actually the largest landslide mitigation project in the world. And at a cost of, I have no idea how much, but no doubt, a tremendous amount of money, because the repercussions, if it goes, even if that's a very unlikely scenario, would be enormous. Yep. Potential collapse of the dam and flooding downstream, et cetera, et cetera. And so, that's kind of a no-brainer in terms of trying to mitigate that. Do you do the same at, in these sort of remote / not remote fjords? Probably not, because Um, it's that much more expensive because they're that much farther away.
Mm.
They're only intermittently populated, right, by cruise ships or recreational like pleasure craft or whatever. And there's a hell of a lot of them. There's a lot of slopes out there that could be problematic.
Mm.
Now, that brings us to an interesting question, and but this may not be where you wanted to go with the question, but many landslides are detectable before they really go. And so, there's one in elsewhere in coastal Alaska called Berry Arm, another fjord, and that one, there's a big giant slope that's moving. I forget how big it is, but it's it's enormous and it's moving. And so the US government has poured lots of money into monitoring that slope, lots of instruments on it, both for science, but also for for the risk that it poses. I don't know if there's actually an early warning system on that slope yet, but it's being monitored. And we have similar ones in Yukon, for example, dangerous slopes that are moving, that are being monitored. But so that one's moving, creeping, and maybe will develop into a catastrophic rock avalanche, where it happens over the course of a couple of minutes. But maybe not. But other slopes don't give any sort of warning signs that you can see with your eyes. So, Tracy Arm, there was no indication that was a slope that anyone would want to pay attention to from a hazards perspective.
Yeah.
Like, you want to pay attention to it because it's at the head of this beautiful fjord, and people go there to look at the glacier and whatever. But it's exactly. But it's not. It wasn't one that was identified by anybody as being, potentially problematic, and that's where I think things get really tricky. So, when I was a grad student, one of the things that I thought would be really exciting, but probably would never happen because it was too computationally expensive or, just difficult, whatever, was to have kind of real-time motion maps from a satellite technique called INSAR to detect ground motion over huge areas, a whole mountain range, so that we could look at, where might we want to sort of dedicate some resources to understanding the risk. And I thought, that'll never actually happen. Well, here we are, 2026, and we're there. I mean, we're not quite at the real-time stage, but we now have in Canada as well as in Alaska, and there are some products in Norway as well, as I think in high mountain Asia, that are kind of mountain range scale or continental scale INSAR, this satellite technique, displacement maps. And so we can go and we can look at where is moving. Now, we're not at the stage yet where we can say, okay, what was it like, how much was it moving yesterday?
Yeah.
But at least for the Alaskan, or for the American one, which is Alaska, the continental US, and parts of Western Canada, that apparently that's the plan, is to get to a point where we can, it's almost real time, like within the last couple of weeks. And one of the amazing things about this, and it's a freely accessible data set. You can go look up ASF, Alaska Satellite Facility, Opera displacement portal. So Opera, just like the thing you go to the theater for, displacement portal, and you can go and click around, and just on a web browser, and look at where do you see colors on this map, and the colors basically mean ground is moving. And one of the things that is, it's really confirmed for me, and this I don't think was really a surprise to anybody in the landslides community, but was confirmation, was that shit's moving everywhere. And like mountains are not static, boring things that don't change, right? The slopes are moving all over the place. And so we can begin to identify, okay, may not be up to the minute, but we can begin to identify where in the last decade are these actively moving slopes. And so that's, I think, one really, really powerful tool for understanding the risk from these kinds of mountain hazards, and potentially, prioritizing them, and then doing, maybe doing something about them.
That's brilliant. Truthfully, I thought I was going to be able to access it in real time, but I don't think my computer's going to let me. So I'll quickly just derail the entire part of this conversation and
The problem is it's a bit of a time suck. Like you won't be able to escape. Can you see my screen here?
Yes. Now we can.
So this is the American one. There is a similar one from the Canadian government, but the interface isn't quite as good. So I'll use this one here. But we can go, like, let's go down to Southern California here, or Central California. And so, you've got
we've got the World Cup going tomorrow. It's going to be thinking about this as I'm watching the game.
Well, yeah, you will be, yeah. So, okay, so what I said was color. Color means motion, basically. And we don't need to get into all the details of what all these things mean in the upper left here. But basically, here we've got this very distinct break in color. Blue on this particular map here is negative. So this means the ground is moving away from the satellite, not vertically, but away. And red means it's moving towards the satellite. Now, okay, so you host a disastrous podcast. What do you think? I'm going to put my mouse over the word that is the answer. What do you think this is?
I think that is, I don't want to say a lake, but
no. I'll turn off the thing here. So this land, right? This is in Southern California. This is the Ridgecrest earthquake. So whenever that was, 99? I don't remember. My knowledge of earthquake history is not that great. But so this represents the ground motion from the Ridgecrest earthquake. And so we can click. So we've got different modes. So the satellites go up and they go down, right? So you'll see that the color is kind of reversed here depending on the way the satellite was going. So if I click here, it will open up this thing at the bottom here, and it'll show us, it calculates for a minute, and it'll show us the time series of the ground moving towards the satellite over time. Or it'll be a step change, right? Because this was an earthquake. So it takes a second here to do that. We'll chat while it's going. But anyway, so what we can do, here we go. So essentially, the ground was totally boring, not doing anything. And then all of the sudden, whenever that was, 2019, so I guess I was 20 years off, which is not a blink of time in geological time. The ground, right where my point was, moved upwards in the direction of the satellite by about half a meter. Wow. Okay, and then it has since done nothing. If I clicked right here on the blue, it will show the opposite pattern. Right. So what we can do with that, here we've got a whole bunch. Here's another one that looks like another earthquake. Wow. Here we've got a whole bunch of color in, I don't know, what is this? The Coachella Valley? I don't. My knowledge of California geography is not that great. Bakersfield, Fresno, etc. What I suspect this is, I don't know for certain, but I suspect this is ground displacement from pumping of groundwater.
Wow. Oh, yeah.
California's had a drought for many years. They may be technically out of the drought now. I'm not sure, but as you pump groundwater out, just like as you pump oil out of the ground gets displaced downwards. And so I think that's what this is. But that's flat ground. That's boring. If we go up to here where we've got mountains and glaciers and all sorts of fun things, we can look at areas where we've got colors on the mountain. Now, not every colored area is going to be true. Some of these may be processing artifacts, but we could click there, and it was a pretty light red, so it won't be that much. Won't be that much change. Oh, that's interesting. This one went up by about 8 centimeters over 3 or 4 years, and then it looks like it dropped back down again. So I'm not sure what's happening there. Huh. We can see volcanoes that are inflating as the magma chamber fills. We can see coastal the coastline rising up after the last subduction zone earthquake, et cetera, et cetera. But on top of that, what we can see is land surface motion in terms of landslides. And so let's see, there's a nice one. I'll turn this off here. We're up here somewhere. So here's, think it's this one where we have, we have motion in opposite directions on, oh, I'm getting an error here. I don't know. Maybe the website's down, but we've got opposite motion on either side of the glacier, right? So we've got the land moving towards the glacier there. I don't think that was the exact one I was looking for, but it's a very similar. Oh yeah, here.
Ooh.
Let's see if we get, yeah. So here, this is obviously a trend, right? Like there's maybe a little outlier here, but right, it was doing nothing in whatever that is, spring 2018, and by fall of 2021, it has dropped down, about
Wow.
13 centimeters or so on that side of the valley, and on this side, and it puts it on the same plot, which is kind of fun. It has risen about 10 centimeters, but in not risen, but moved towards the sensor. So in other words, if the satellite was between those two, the satellite would be over here somewhere. One of the slopes is moving like this, so it's moving towards the sensor, and the other one is moving away from it. So anyway, these kinds of tools are
wow.
A total game changer in how we can understand how mountain landscapes are really dynamic. And so you couple that with seismometers all over the place, and then we can start to talk about early warning and that sort of thing.
Yeah, and that history of the mountain and knowing the people around and the exposure and the potential for hazards, like that is game changing for sure. Like that's
one of the issues, if from a Canadian perspective, that keeps me, I don't know if I would say keeps me up at night exactly, but certainly I worry about is not so much cruise ship passengers, because we do have cruise ships in Canadian waters, but is oil tankers. We're talking right in these last 6 months or so about a potential new pipeline from Alberta to the coast. Just last week, maybe 2 weeks ago, there was some leaked reports from the Alberta government about potential termini for pipelines, 5 or 6 potential options, on the north coast. And those, although the topography of those coasts, where Kitimat is and Prince Rupert, et cetera, it's not as high or as steep as Tracy Arm necessarily. Doesn't have those glaciers at the head of them, but nevertheless, those fjords are landslide prone. The federal government has been doing a wonderful job over the last decade or so, mapping all those fjords to understand, well, what is the landslide risk and the landslide hazard, I should say, and the potential for tsunamis. And there are dozens to hundreds of landslides that have been mapped in some of these fjords, under the water. That maybe are very old, but until we have a good handle on how often they've occurred over the last say 15,000 years, it's very hard to predict what the risk to municipalities, whether that's Port Alberni or Prince Rupert or whatever, but also to this kind of what did I call it, transient intermittently remote, like if just imagine a tanker, no matter how triple hulled it is, being hit by a 100-meter wave.
Yeah, and we're still talking about the spills from long ago.
Yeah,
ecosystems are going.
During my PhD, I did some work in out of Cordova, Alaska, which was one of the most hard hit towns from the Valdez oil spill in was that 89.
Yeah.
And even when I was there, 2008, I think it was, right? So nearly 30 years after the fact, that fishing community had not recovered because there was a fishing industry there, but the industry that had been there was gone. Right? They were fishing for different species, far fewer people making their living from the sea. And that's to say nothing of the indigenous cultural importance of marine environments.
My background is disaster recovery for the sudden hazards. So your fires, your floods. Oil spills are a completely different game because it's a pay or the polluter has to pay is effectively what happens. And just as you described, if there is any sort of destruction from, a tsunami, like so many of those coastline communities, indigenous, non-indigenous, they would have to endure a lot of those things. So that would definitely keep me up at night as well. Now that I think of it, oh my god.
One of the, I suppose one of the positives here is that, these big tsunamis in fjord environments, or maybe I should say landslide tsunamis, are, they're very big, they're very dramatic, but they do dissipate pretty quick. So, by the time that this tsunami had reached Juneau, which was, I don't know, 150 kilometers or something as the fish swims, the wave was only 30 centimeters high by that point, right? So like if you were on the beach, you'd probably notice it, but it wouldn't really pose much of a threat. It's really if a ship is in, the upper part of a fjord, if the wave hits, if that's where the landslide hits, that's where the danger really, really exists. And so, if there is a desire in this country to, double, quadruple, quintuple, whatever the number of ships holding, fairly toxic materials in some of these steep fjords, we really ought to get a better handle on what the risk actually is.
Yeah, well said. I totally agree. There's a paper there somewhere for us to.
Oh yeah, well, absolutely.
Yeah. So let's actually dive into just a few of those quick thoughts. Who do you say? Well, actually, no. Let's take one step back. What's the role of cruise ship operators? And I mean, we can even get into like the people who ship and move these boats. What role do they have in, I guess, preparedness? Like, do you think that they need to be the ones saying like we can't go here because there is, or what's your thoughts generally?
That's a good question, and I don't know is the short answer. I'm not well versed in marine architecture or how cruise ship captains or the pilots that help the cruise ships navigate these fjords. I think they bring a pilot on board for these, especially tricky areas. I don't really know how that world operates. I've never been on that kind of a cruise ship. One of the interesting things, though, following the Tracy Arm event, is that I don't know, 6 or so. I'm not going to say that dual number that my kids will get all excited about, but 6 or so cruise ship companies announced that they're not going to sail into Tracy Arm for the 2026 season. A few of them said 2027 as well, and they're going to stick to Endicott Arm. And there may be a few reasons why they decided not to go into Tracy. There may have been indications from NOAA or something like that it was too dangerous for them to go map the fjord bottom. I don't know the details of that, but they've decided, okay, we're going to go into Endicott Arm. One fjord to the south, pretty similar. It's a bigger fjord, but it has a big glacier at the terminus, similar glacial retreat pattern, et cetera, et cetera. And so, if we were to go online now and look at the ship tracking websites, we would see, mid-June, 3:30 in the afternoon, Alaska time, or maybe 2:30. I forget if they're 2 hours behind now or 1. We would see probably 10 boats in Endicott Arm. Not all cruise ships, right? Some of them are going to be smaller vessels, but we're going to see it's going to be full. And is Endicott necessarily any safer than Tracy?
Wow.
I mean, maybe, but maybe not. And that's part of the problem is we don't actually know.
Wow.
We're avoiding, or not we, those boats are avoiding Tracy Arm because this big event happened. And, maybe there is a big block of rock still lodged up there that's going to, threatens to come down. But the whole point of, or one of the key messages from our Tracy Arm study was that, we didn't have warning, at least from a geological perspective. We had a little bit of warning from a seismology perspective in the, about a week beforehand. But without a dense array of seismometers, which surprisingly doesn't exist in Southeast Alaska, nor along most of coastal British Columbia for that matter.
Yeah.
It's really hard to say.
Yeah. Yeah. And I mean, even if we do have some of those warning systems, and we saw how fast, if you're in that fjord, it doesn't matter. If you're going into the fjord, I mean, probably still doesn't matter. But if you're like, a couple kilometers away outside of the fjord, that's the time where really that we could probably save lives. I mean,
and in
wow.
if a boat, like there was a cruise ship in Tracy Arm, it was close to the end of the fjord, and it was a fairly small cruise ship, 150 people aboard, and they certainly felt the wave. They saw lots of turbulence, and sort of the water was kind of violent, but it wasn't a catastrophic wave. To use the word catastrophic in the sense that you would use it, it wasn't. It didn't flip them over or anything. So a boat, large boat out farther out in, away from the mouth of the fjord, it would probably be fine. Some drinks would get knocked over, etc. But it wouldn't capsize. But if it was within a few kilometers, which keep in mind that's where they're going, right? They want to go see the head of the fjord where the glaciers are. That's where it gets really, really dangerous. Now,
wow.
These again, I'm not exactly well versed in this, but in climate, in anything climate change related in terms of impacts, it's the insurance industries that are quite often leading the charge in terms of mitigation, or not mitigation exactly, but adaptation, and maybe that'll be the case here. Maybe the insurance industries are going to be the ones to force the scientific studies to be done to say, okay, which fjords are probably safe, which fjords are maybe best avoided.
Mm-hmm. Yeah, if you want to go sail there, you can. You just don't have insurance, and then everybody goes, okay, yeah, we're not sailing there for sure. That's. I'll just pause it there. Okay, so I do recognize the time. So I have one final question, and it's something I've really been thinking about for the series of hazards that I've been learning about and everything like that. Are landslide tsunamis a new threat, or because we're getting better at monitoring, we're getting better at learning how things happen, we have more data, are we just becoming more aware of them? Is it more like a climate change, or is it a data-driven phenomena that we're learning more?
So in our paper, we cataloged the tsunamis greater than 50 meters of run-up elevation that have occurred over the last century, and there's a little over 24 of them, and something like 2/3 of them, the vast majority of those 24 have occurred as a result of landslides, and something like 2/3 of those are in environments where glacier retreat and permafrost thaw are probably a contributing factor. Now, 24 is not a very big number, and so it's probably a little hard to get a sort of a statistically robust answer to your question, but it seems that yes, they're getting more common. In the last decade we've had 3, 4, 5 of these 100-meter plus tsunamis occur in Greenland, 2 or 3 in Alaska, in British Columbia. These are almost certainly getting more likely, and probably will get more likely going forward. Now, I haven't seen papers on this, but I suspect the same is true in terms of the tsunamis generated in lakes from landslides on like otherwise dry land. I don't know if the number of these tsunamis has increased, but I suspect it probably has, but probably will more so in the coming 20, 30 years.
Yeah. for all the reasons that we talked about regarding climate change and everything like that. Thank you for everything. This has been a wonderful conversation, and I think it really has gotten me thinking about exposure, bringing people to areas to see the natural beauty of the world at the same time that there is risk associated with that. Um, so,
My pleasure. Not, I'll bring it back to Alberta here. A year ago, oh wow, like almost exactly, maybe even to the day, we had the Bow Glacier Falls rockfall in Banff National Park, which killed 2 people. And that was a tiny rockfall by landslide standards. It just happened to occur, at the wrong time, at the wrong place, where in a spot where that is incredibly popular with hikers, because easy hike, you can get into some spectacular scenery very quickly. And in discussions with a consulting firm in Parks Canada, I've been thinking about, well, how do we manage these, or do we manage these landslide, or these hazardous environments in what is the backcountry? People go to see these amazing landscapes, and they're amazing partly because of the landslides, right? That's what's making these environments steep and spectacular, or at least that's one of the reasons. And so, this is a really tough question. Sometimes I tell my students, like, as a geoscientist or environmental scientist, we have the easy job. We can go and we can reconstruct the event. We can figure out, okay, what happened? It's easy for us to say, oh, we shouldn't build there anymore. We shouldn't rebuild after Katrina. We shouldn't build in the Bow River floodplain because it's going to flood or whatever. It's the politicians, the policymakers that have the really hard job, right? They've got to turn the scientific understanding into some kind of decision, but it's not solely based on the science. It's not just the hazard, it's the risk. And that's a really, really tough one to crack.
Totally agree. I'm not in that world anymore because it's too hard. So thank you for everything, Dan. Before we depart, where can people reach you if they have questions, if they want to get that paper?
Sure. So my email at the University of Calgary is daniel.shugar. Sugar is like what you put in a cake, but with an H. So daniel.shugar at ucalgary.ca. And as we talked about at the very beginning, I'm at Watershed Lab on Blue Sky. So at watershedlab.bsky.social.
Well, thank you very much.
But I don't use that all that much.
Yeah, perfect. Well, thank you. I appreciate your time, your consideration, and that's all we got for today.